In Chapter 18, we're going to look at two main things. We're going to introduce, we're going to go back to thermodynamics. So thermodynamics in Chapter 6 focused mostly on delta H. And we learned about the first law of thermodynamics, which was that energy has to be conserved. It can't be created or destroyed. So energy is just transferred from system to surroundings. We're going to learn that there's a couple of more pieces to thermodynamics. We're going to learn that there's a second law and a third law of thermodynamics. And this is going to center upon the other primary thermodynamic term. We have enthalpy from Chapter 6, and now we're going to introduce entropy in Chapter 18. And entropy looks at disorder in systems. So we're going to start Chapter 18 by looking at entropy in the second law of thermodynamics, and then we're going to add in another video some principles of the third law of thermodynamics to better understand what's going on. And then finally, at the end of Chapter 18, we're going to apply this to free energy and equilibria. So to get started, we have to define some terms, and the first thing we're going to look at is we're going to look at spontaneity. Okay, we're going to look at, sorry guys, we're going to look at spontaneity and what spontaneity is. So a spontaneous process is a physical process that occurs by itself. And that may seem a little bit obvious. If it's spontaneous, it happens by itself. But what I think students tend to get confused with when it comes to spontaneity is they get confused with something that's, they start to think like, well, if it's exothermic, meaning it gives off energy, then it must be spontaneous. The universe always wants you to give away energy. And anything that's lower in energy is going to be more stable. However, when it comes to spontaneity, we have to start to think of this now in terms of not only enthalpy, but this new thing we're going to define called entropy. So, for example, spontaneous process would be like a rock falling down a hill. A hot piece of metal or a hot brick heats up water. And then one that you might think of chemically would be just that if you put some iron outside, it rusts in air. So these things, they just, if you put them out at a given temperature, it just happens on its own. So a spontaneous process occurs by itself. So then a non-spontaneous process is basically a physical process. So I'm going to put little things here. So it's a physical process that requires an external force. And so examples of this would be, pushing a rock up a hill. Or the process of purifying rust to get pure iron back, right? So if iron rusts spontaneously in air, you have to put energy in to bring that iron back to its pure form. So now one of the things we're going to look at is we're going to look at the relationship between spontaneity and exothermic versus endothermic processes. On this slide, we have a concept question, and we're going to start to think about spontaneous processes and something you already know, exothermic versus endothermic. So let's kind of take a look at this and just start to think about things. So the first part of this question says, write the chemical equation for the evaporation of water. So what we have is we have H2O liquid going to H2O gas. So now we have to think about, is this process exothermic or endothermic? So is the delta H a positive or a negative? Well, when we boil water, for example, so when we take water and we purposefully make it go from liquid to gas, we have to put in energy, right? So we have to heat it up on either on a stove or with a hot plate or a Bunsen burner. And then that energy goes into the water and overcomes the intermolecular interactions. So what we're basically doing when we evaporate or boil water is we're overcoming intermolecular interactions. And to do that, basically we're pulling the molecules apart. The delta H has got to equal a positive, meaning to get water to evaporate into the gas phase, we have to overcome the intermolecular interactions and then separate them into this phase where they're not interacting with each other anymore. Now here's the important question. A lot of you guys would say, well, if the delta H is positive, then boiling water is not spontaneous. You have to apply an external force to make it boil. You have to put it on a hot plate. But if you think about it, though, if you just put water in a cup on the bench in the lab and you let it sit there for 3, 4, 5 weeks, when you come back, that water is going to be gone. So evaporation at room temperature, it's very slow, but it does happen. So this process is actually spontaneous, even though we have a delta H that's positive. So that's what this next part of the question is getting to. Does the enthalpy of the reaction support the fact that the reaction is spontaneous? Well, I think in our minds it would be no, because normally we think of an exothermic reaction being where the energy of the products is lower than the energy of the reactants, meaning we're going toward more stability. Is a good thing. The universe wants that. But in this case, our products are at a higher energy than our reactants. So from the delta H perspective, this thing shouldn't be spontaneous. Things don't want to go to higher energy normally. So now what we have to think about is, well, how can this possibly be? How can it be that evaporation is spontaneous, but yet the delta H doesn't support that? And we're going to have to introduce a new principle into our understanding of thermodynamics, and that is the disorder, or the entropy. So in this example, what must be driving this to happen is that there must be some preference for the water to be in the gas phase, because that's the only thing that could support this positive endothermic reaction to happen. This delta H that's positive. There has to be something that's driving this thing to a higher energy to make the universe happy, and what it's going to be is the disorder, or the entropy. It turns out that the universe likes things to be disordered and not organized, and by moving in that direction, we move to increased entropy. So in the next couple of minutes, we're going to define entropy, and we're going to look at the second law of thermodynamics. So we're going to define entropy as a measurement of how dispersed. Spelled that wrong. As a measurement of how dispersed the energy of a system is. Sorry guys, give me 1 second. I just got to get back to where I was. Of how dispersed the energy of a system is. And so basically this is a measure of the disorder. So, for example, if you think about it, if you want to think about just phases, for example, and you want to think about entropy, so solids are going to have the lowest entropy because they're the most organized, which is going to be less than liquids, which is going to be less than gas. So if you think about the energy that's contained inside of an atom, all that stored energy, in a solid, that energy is well organized, and they're all the atoms are locked into a crystal structure. It's very predictable and very organized. When you go to liquids, we start to the atoms can start to move, and now we don't know where every single atom is going to be anymore. They're in a contained, like in a cup, for example, and it's contained, but we can't go in and say at this one specific point in space there's going to be an atom there all the time, because the molecules are moving around freely inside the liquid. And then you can imagine that gets even more disordered with gas, because now all of that energy is dispersed over an even larger volume in the gas phase. So another way of thinking about this is that it's also a measure of the dispersity of energy. So the example in this case is, you have a hot cup of coffee. So you make a nice warm hot cup of coffee and you put it on your bench top. What that coffee is going to naturally tend to do is it's going to tend to heat things up around it. It's going to heat up the air molecules that surround it. It's going to heat up the countertop that it's sitting on. As that heat gets transferred to the surroundings, all of the molecules start to vibrate and move faster. Basically, the temperature rises from the molecules around it. That transfer of energy results in more atomic motion of the air, of the molecules, and that also leads to a bigger dispersion of energy. So entropy is a measurement of how dispersed the energy of a system is. And its units, and this is important, the units of entropy are in joules per Kelvin. And another thing that's important about entropy is that it's a state function. So we remember, if you have to go back to chapter 6 and think of this, enthalpy is also a state function. Like enthalpy, entropy depends on where you start and where you end. So it's dependent on the start and endpoints. So you can take a very circuitous route from point A to point B, but entropy only matters on the difference between where it starts at point A and where it ends at point B. So we can assign then, just like we can for delta H, we can say, well, delta S is going to equal S final minus S initial. Now S is the symbol for entropy. So that's important. So for example, if we had 1 mole of ice or solid water, that has an entropy, or an S, equal to 41 joules per Kelvin. And then if we look at the entropy of 1 mole of liquid water, H2O liquid, the S in that case is equal to 63 joules per Kelvin. So if we want to know the delta S for the phase transition, meaning if we go from H2O solid to H2O liquid, then the delta S in this case is going to equal 63 joules per Kelvin minus 41 joules per Kelvin, which is going to give us 22 joules per Kelvin for the change in entropy. So let's look at the second law of thermodynamics, because the second law of thermodynamics is going to allow us to put some some rules on entropy. Basically, it's going to tell us what we can and cannot do with entropy. So when it comes to the second law, the total entropy of a system and its surroundings must always increase for a spontaneous process. So what this is basically saying is that the entropy will always go up if you look at the entire global systems and surroundings for a spontaneous process. And so if we look, we can bring back one of our rules from the first law. So energy can't be created or destroyed. So I'm just going to remind you guys that that's the first law. And so now we can kind of write a rule for entropy in the same sort of light. So entropy can be created, meaning we can make something more disordered. Or another way of thinking about this is, if you want to do it, is produced by a reaction. But it can't be destroyed. So entropy is a one-way ticket. You can only make entropy, meaning you can only make a system more disordered, and a system and its surroundings more disordered. So even if you have a process where you make the system more ordered, the surroundings will still get more disordered overall. So the example I like to kind of say for this is my daughter, who's 2 years old, she has a whole bunch of these mega blocks, and she loves playing with mega blocks. And they come in this big bag. So, she got this big bag of mega blocks. And so my daughter is a good example of entropy, because what she does is she takes that big bag of blocks, dumps it on the floor, plays with things. She does build some things, but at the end of the day, those blocks wind up everywhere. And so she is making disorder. So the universe is happy by what my daughter is doing. And then what I do is I have to go and clean it up at the end of the day. So I go and find all the blocks and put them back into the bag. So one would think that all of the disorder she just created is now gone, because I've gone and I've taken and I found all the blocks and put them back into the bag. However, if you think about it, in the process of me going and putting all of those blocks back into the bag, I was doing all kinds of chemical processes biologically. I was respiring, meaning I was taking glucose and turning it into carbon dioxide and water. So the energy that I had to put into going and organizing all of those blocks actually leads to an overall increase in the universe's entropy, because I've now taken all kinds of molecules and turned them into gases, and I've also disturbed all of the molecules in the room. So in that process of me cleaning up, even though it was not necessarily spontaneous for me to put those back in the bag, overall, and I decreased the entropy locally, the rest of the universe experienced an increase in entropy. So now let's look at an example of entropy, and let's look at the example of entropy and phase changes. So in the case of, we have like a beaker, for example, and in this beaker we have some H2O liquid, and it's going to H2O gas. So we have a phase change. So the entropy change of the surroundings can be defined as the heat flow, meaning how much energy is transferred, divided by the temperature. So this is equal to Q over T. And so the entropy created by the system plus this entropy of the surroundings, Q over T, is going to equal the total delta S. So basically, we're making entropy by evaporating the water, by making the water go into the gas phase. So this is the entropy created by the system. And then also the surroundings have an entropy change, because we are transferring heat from the surroundings to the system. So this whole thing, the system and the surroundings, is equal to the total delta S. And so we can say that since entropy can't be created or destroyed, that the delta S has got to be greater than Q over T. So what that means is that the total delta S has got to be greater than just the simple change of the system and the surroundings. So when we look at entropy changes for a phase change, what we wind up getting is that that delta S is equal to Q, which is the heat transferred into, which is the heat that goes into the system, divided by T at a constant temp. So this is the heat that goes in, and this is at a constant temperature. So the way that we can kind of think of this is that this is equal to delta H, which is the heat associated with a phase transition. And we remember that phase transitions happen at a fixed temperature. I should actually make these capital T's because it's temperature. So because phase transitions happen at a constant temperature, we can say that, well, the delta H for that phase transition divided by the temperature at which the phase transition happens is going to be equal to the total entropy change for that reaction. So in a couple of seconds, we're going to look at that as a lecture problem. But first, I'd like to just go over a couple of things in terms of predicting entropy changes. So this is how we can predict an entropy change with a phase change. Let's look at entropy and disorder in reactions. So we talked about phase changes already. So when it comes to phase changes, we said that that solids have the lowest entropy, which is less than liquids, which is less than gases. So you can predict whether entropy is increasing or decreasing by knowing what phase is going into or out of the reaction. So with a phase change, if we're going from a solid to a liquid, then we're going to have an increase in entropy, or from a liquid to a gas. So now another thing we can do is we can think about heat transfers. So for example, what happens if we heat up a gas? So the example here would be heating a gas, or it could be heating anything, but a gas is the easiest one to think about. As you increase temperature of a gas, we know that we're going to get a corresponding increase in the volume. This is according to PV equals nRT. So from that process, we know that if we're increasing the volume, that gas is now spread out over a larger area, and so we get an increase in entropy. So whenever you increase, so the rule is that when you increase temperature, you're going to always increase entropy. You can kind of think of that also with things like water, right? So as you heat the water up, the molecules are going to start to move faster, and they're going to start to become less ordered than if they were cooler. So another good one to think about is changing the number of moles of gas. So as you increase the number of moles of gas, you're going to increase the entropy. So a reaction that produces gas, like for example N2O4 gas goes to N2NO2 gas, this is going to result in a gain in entropy. And then the final one is dissolution. So in the aqueous phase, so when you have a solid or a liquid that goes to the aqueous phase, you're going to increase entropy. And the reason of this, of course, is because the solid or liquid is very well organized. When you dissolve that into a solution of water, now you have this homogeneous mixture where you have water molecules and your solute. So now before, where everything was neatly organized, you had water in a cup and you had your solid in somewhere else. When you mix the two of them together, they become completely disordered into each other. So dissolution of things into aqueous phase leads to an increase in entropy. Okay, so let's look at a problem where we have to calculate the entropy change of a phase change. So the equation that we introduced for this was that the delta S of a phase change is equal to the delta H of whatever the phase change is divided by the temperature at which the phase change occurs. So this is going to be the equation that we use whenever we get a phase change. And the reason why we can use this equation is because something kind of interesting happens with phase changes. If you guys remember the graph, so we can flip to the graph. This is what a heating curve looks like for going from a solid to a gas. So if you kind of look at this, let's start to interpret this curve qualitatively before we look at this quantitatively. So what you notice is that on this side we have the standard entropy, and then on this side we have temperature. So as we increase temperature, we know that this should increase entropy. We said that that was one of the four things that should increase entropy, increasing temperature. And we see that. Over the entire graph, the entropy is going up. But there are a couple of places where the entropy goes up a lot. Entropy rises rapidly. And we notice that this is associated with a phase change. And phase changes are special because what happens at a phase change is we're putting energy in, and that energy is going into breaking, so the energy breaks the intermolecular interactions at a phase change. So the reason why we get this rapid rise in entropy is because we're going from a liquid where the molecules are fairly strongly interacting with each other to a gas, for example, where the molecules are not interacting with each other at all. The same thing with a solid to a liquid. With a solid, we're in a well-ordered crystal structure, and then after we're done with the phase change, that well-ordered crystal structure is gone, and now we have a liquid with molecules moving around. So we see it in a very short temperature, in a very short range of temperature, actually at one temperature, we get a very dramatic rise in the entropy. And that's because at this temperature, we're converting it from one thing to another. So you have to remember with phase changes that if you look at a heating and cooling curve, that the phase change happens at a specific temperature. We boil water at 100 degrees Celsius. So that's why we can use the equation that we have in this page, because we have a fixed temperature where we're boiling the water, and the energy is purely going into separating the molecules. So that's where this delta H over T equation comes from. So now let's look at the problem itself. So we have liquid ethanol at 25 degrees Celsius has an entropy of 161 joules per mole Kelvin. If the heat of vaporization at 25 degrees Celsius is 426 kilojoules per mole, what is the entropy of the vapor in the liquid? So the first thing we're going to do is let's calculate the delta S associated with the phase change. So this is the delta S of vaporization. So in this case, our delta T is 42.6 kilojoules per mole. And our temperature, and in this case, our temperature, we have to convert it to 298 Kelvin. So now we're back to chapter 6, where all of our temperatures have to be converted into Kelvin because we need to be on an absolute scale. And if you remember, the units of entropy have to be in joules per mole. So, joules per Kelvin. So we have to convert this kilojoules per mole into joules per mole. So we're going to get, there was a 42.6 there. So we're going to get, what is it? Let me just take a look at my notes. So 42.6 times 10 to the third joules. So we multiply that by 1,000, divided by 298 Kelvin. And when you do this, we get 142.9 joules per Kelvin. So that is the delta S of the vaporization. Now, we have to understand what the problem is asking us for. So if we go back to our graph, here, we have the thing sitting here at a liquid, and according to the practice problem, as it sits there at a liquid, its entropy is 161 joules per mole Kelvin. And then we just calculated, well, what is the phase change for going up to the gas phase? And that is 142.9 joules per mole Kelvin. So in essence, what this is asking for is, this is asking us for what is the entropy of the vapor in equilibrium with the liquid. So what we have to do is we have to take our 142.9 joules per Kelvin and we have to add to it the original 161 joules per Kelvin, and then we get 303.9 joules per Kelvin. So that up here is the 303.9 joules per Kelvin. So you can see what I'm talking about. The delta S for this process, which is here, is the difference between where it starts and where it stops. So this is the liquid, this is the gas, and the delta S of the phase transition is that 142.9 joules per mole Kelvin.